Welcome. I hope you had a good breakfast, and now we'll have some physics. So first I want to start off by thanking our ever-growing list of sponsors. It's really gratifying to have you show your confidence in the school. And let me just tell you a couple of things that are going on at the moment. So those of you who are New York Times subscribers, 2 weeks ago, Sunday, I believe, saw in the New York Times Magazine a feature on Eric Grignot's work on melting of the glaciers. Slightly frightening, but I think quite important. So we're very proud of that work. And we're also like to mention Steve Davis's work in Earth System Science, that he's studying the economics of production in China and who should really be taking credit for the CO2 production that goes on in China. So one statistic is that if you filter out the goods that they ship to us, they actually consume far less CO2 than we do. In mathematics, we have a couple of nice things going on. Professor Richard Schern was just elected to be the vice president of the American Mathematical Society. And the department is starting a really impressive program called Math CEO, a program for socio-economically disadvantaged middle school students from Santa Ana Unified School District to help them excel in STEM fields and promote higher education. So we're hoping that gets off to a great start and looking forward to more upwardly mobile students attending the University of California. In the chemistry department, Professor Sergei Nizhgorodov just last week was named a fellow of the American Association for the Advancement of Sciences for his outstanding contributions to aerosol research. And Jen Prescher was selected as an American Chemical Society Rising Star. So we're always proud of all of our faculty, but those are the two we're mentioning today. And now, moving to physics, which is our focal department this morning. I think many of you have already seen, and those of you who haven't, I hope you'll visit Fred Reines Hall to learn more about UC Irvine's contribution to neutrino research around the world. And in particular, the 2015 Breakthrough Prize in Fundamental Physics acknowledged the work of UCI neutrino physicists Hank Sobel, Bill Kromp, Michael Schmee, Sunuchi Min, Jeff Griskovich, and Mark Vagans. And of course, none of this work wouldn't have happened without the founding work of Professor Fred Reines, who started neutrino physics at UC Irvine and was awarded the 1995 Nobel Prize for first observing neutrino. Of course, none of this work happens, well, not much of this work happens without great graduate students. And my focus as dean is trying to help raise money to support graduate students, and anyone would like to leave a contribution, it would be very, very welcome. And if you'd like to talk to me personally, I will certainly make time. So graduate students do a large fraction of the wonderful work that goes on in our school. So without further ado, I'd like to introduce today's speaker, Professor Daniel Whiteson. Some of you have been enjoying his work to explain particle physics to the broader audience in the form of cartoons. I don't know how many cartoons he'll be showing today. I didn't get to see the talk. We'll find out, I guess. Daniel received his bachelor's degree from Rice University and then his PhD from UC Berkeley. He works in the field of experimental particle physics, especially as part of the ATLAS collaboration at CERN. So UC Irvine plays a large role in the ATLAS collaboration, and that's the detector that about a year ago, is it 2 already, observed the Higgs. 3 already? Oh my gosh, time flies when you're as old as me. 3 years ago, observed the Higgs boson. So we're very proud of UCI's contribution to that work. In 2014, Whiteson set out on a mission to conceive a much larger particle detector, and that's what he's going to talk about today. the largest particle experiment ever constructed. So without further ado, I'll turn the floor over to Daniel.
Good morning, everybody. Thank you for coming out this early to hear about particle physics. So today I'm indeed going to be talking about the largest particle physics experiment ever conceived, as if a $10 billion 33-kilometer experiment in Geneva wasn't big enough. And the particle physics experiment is designed to search for cosmic rays. And if the word cosmic rays scares you, or you think, I'm not an expert in cosmic rays, am I going to understand? Don't worry, I have a confession to make, which is that I'm not an expert in cosmic rays either. This is a new project for me in a new direction. As Ken told you, my day job is to work at a particle collider in Switzerland. But cosmic rays are particles, and they're mysterious. And particles are always good ways to probe the big questions of the universe. And I'm a particle physicist, so I'm interested in the big questions of the universe. So first I want to tell you about how cosmic rays are important for thinking about the universe and how it works. And when I say the big questions of the universe, I really mean the big questions, the questions that everybody can understand. You don't have to be a particle physicist to understand why we might be interested in how things work or how things are made of. Then again, if you say the big questions, some people might think of this, who's going to be the Republican nominee, or does Ben Carson really know what he's talking about? Other people, when you say the big questions, they might think about things like this. Here's a question posed in 1974. What is it like to be a bat? This is one of the most cited works in philosophy ever, right? The short answer is, we'll never know what it's like to be a bat. All right. That doesn't disappoint all of you. But this is the question that I think when I say the big questions. I think, what is the universe made of? I want us to understand how things work so we understand our place in the cosmos. I want to discover something which changes our relationship with the universe. Discovery on par with quantum mechanics or relativity, or even the fact that the Earth goes around the sun rather than the sun goes around the Earth. These kind of big questions about the context of the place we find ourselves in. Okay, and so imagine that you were the first person to think of this question. What is the universe made out of, right? Sort of a large question to start with. But if you were the first caveman or cavewoman scientist and you rolled out of your cave one day and you thought, what is the list of everything in the universe? You might start to answer that question with just a list and say, well, there are rocks, and there are plants, and there's water, and there's fire. And the Greeks had this sort of approach. They said, let's try to make a list of things that are in the universe. But there's a very long list of things in the universe, right? You say earth, water, fire, and then you see a giraffe. And you say, well, where's that in my category? And then you see something else. And very quickly, your list grows to be very, very long. In order to have a really interesting answer to this question, not just an answer which is a list, you want a simplification. You want to say, I want a short list of things from which I can make anything. And that, of course, is the triumph of a description like the periodic table. From this list of about 100 things, anything that you've touched or tasted or interacted with can be made, right? The universe is basically built like Legos. It's an astounding achievement to go from almost an infinite variety of things we discover in our universe around us to 100 basic building blocks. And then fast forward, and we have the standard model, where we have a much smaller set of fundamental particles from which we can build all the elements in the periodic table, from which we can build iPhones and fire and all those things. So we have a few particles that we call matter particles, these quarks, and a few leptons, and then a few bosons that help them talk to each other. So that's a really astounding achievement. We've boiled down matter to just a few particles. And of these 12 particles that we've discovered, you only really need a few of them. You need the electron, you need up quarks and down quarks. With these two guys, you can make neutrons and protons. You sprinkle enough electrons around, and you can make anything on the periodic table. Okay, so we've made a lot of progress, but there are still questions, right? There are questions about these things that don't quite make sense. And the way we've made progress is by following this strategy, which is looking for the loose threads. You have a good picture of the universe, but sometimes something doesn't quite add up. A small mystery remains. And it's by finding that little mystery and tugging on it until you fully understand that you can make dramatic, revolutionary discoveries that change the way we think about the universe. For example, we have been studying matter for hundreds of years. We think we have a pretty good understanding of it. It turns out that the kind of matter we've been studying only accounts for 5% of the stuff in the universe. How did we figure this out? Well, some people were looking at the way galaxies rotated, and they didn't quite rotate the way we expected. They were rotating much faster than we thought. And this was a mystery for decades. People were thinking about it, wondering about it, till finally they understood that the explanation was that there was a lot more matter in those galaxies than they thought. Later, people were looking at the way the universe expanded and discovered that there's a huge amount of energy pushing the universe apart. So tug on those cosmic strings, those loose strings, and you can unravel an enormous mystery. So that's the motivation, right? Find something that doesn't make sense and pull on it until you understand it, and there could be a universe-changing insight there for you. So the one I want to talk about today, the loose string that I want to pull on today, is that of particles from space. That's what we call cosmic rays. Particles, the Earth is constantly being bombarded by particles from space, created by the sun, created by other things in our galaxy. There's a huge number of particles that hit our atmosphere. Fortunately, our atmosphere filters most of them out for us, so we're not all getting cancer. And the interesting thing, the mystery about them, is the energy they have. So here's a graph, and I won't show you a lot of graphs today, but this one I think is really important. This axis here is the energy of the particles in electron volts, and this is how often we see them. So at lower energies, down here, we see a lot of particles, like 1 per square meter per second. Okay, so in a square meter, every second you see one of these particles at this energy of 10 to the 10 electron volts. Now, how much energy is 10 to the 10 electron volts? Well, for comparison, the LHC operates, the Hadron Collider at CERN operates at energies around here. So about 1,000 times less than the LHC. Now, if you want to go to LHC energies and above, you get about 1 particle per square meter per year. Down here, it's 1 particle per square kilometer per year. But look at these energies. These energies are crazy. This is 1,000,000 times more energetic than the particles we make at the collider at CERN. So as humans, we're pretty impressed with our capacity to build very energetic particle colliders and smash them together. But somewhere out there in the universe is an accelerator which dwarfs our capabilities. It's shooting particles at us with 1,000,000 times as much energy as anything we can create on Earth. And you might think, well, that's fine. Obviously, there are things out there in the universe that are more powerful than us, right? Stars and suns and galaxies and all sorts of things. That's true. But if you ask astrophysicists, what's the highest energy particle we should ever see coming at us from space? Take everything you know, take a supernova and have the particles explode and then whiz them around a black hole and soup them up in any way you know possible. Then they tell you, well, you should never really see anything above here. But we do. And it's not just like we see them a little bit above here. We see them at 1,000 times as much energy as anybody predicts. Right? Something out there in the universe is capable of shooting particles 1,000 times more energetic than anything we possibly understand. So there's no explanation for the energy of these particles. We should not see them, and yet we do, which means something out there is capable of making particles, and we don't know what it is. The other really interesting thing about these particles is that the universe is mostly opaque to them. They don't just fly across the universe without being touched. They see the universe as pretty foggy. They interact with photons left over from the Big Bang, and they get slowed down. They slow down pretty quickly, in fact. So if one of these particles is created at very, very high energies, it can't travel very far, which means if we're seeing them, then they're being made somewhere nearby. So somewhere, something in the universe, not very far away, that we've never heard of, some crazy new object, is capable of creating particles with extremely high energy. So this is a cosmic mystery, right? This tells you there's something out there in the universe we don't understand. What could it be? Well, it could be something mundane, like a new kind of star we haven't seen before that has a particular time in its life when it shoots out particles. It could be. That'd be interesting to astrophysicists, but maybe not other people. But there could be other more spectacular explanations. So here's a few papers, for example. Here's one written by a guy at the Institute for Advanced Science, and he suggests that there could be aliens, that's right, aliens, doing particle physics out there in deep space with particle accelerators the size of solar systems, and we could be seeing the pollution from their particle experiments. This is not a crackpot, okay? This is a guy at the, this is Einstein worked here. These are real ideas. Here's another idea. Somebody said, could we tell if the universe was actually a numerical simulation inside some massive computer? Well, that's an interesting question, right? And they propose that the distribution of the highest energy cosmic rays could tell us about the discretization of that simulation, right? So these are obviously important questions. What we're going to discover, I don't know. But I'm hoping I'm hoping that when we tug on this cosmic mystery, we'll learn something crazy, something that changes the way we think about the universe itself. Okay, so how do we actually do this? How do we see these particles from space? Well, fortunately, the particles, when they hit the atmosphere, they don't penetrate all the way down to the ground, or they'd be like death bullets from space. What happens is they bang into other particles in the atmosphere, and they create a little explosion. So one particle at very, very high energy becomes 2 at half that energy, becomes 4 at a quarter that energy, and they come down to the ground. You have a massive, what we call a shower of particles that wash over the surface of the Earth, all in a very small amount of time. And it's an enormous number of particles. You have one particle at 10 to the 20 electron volts can turn into 10 to the 20 particles at 1 electron volt. So a huge number of particles. So this is a sort of a cartoon version. You see all these particles created, and the way you see them is you build a bunch of detectors on the ground that can see particles, and you just wait. So this is like a massive camera, right? And the state of the art in terms of experiments to see these things is called the Auger experiment. It's in South America. And they have 3,000 square kilometers of land. And they've dotted it with these detectors here. They look like this. They're just a water tank. And it's a special kind of water, and it can see a particle flashing through it. It makes a flash of light when a particle goes through it, and they can detect that. So these are really nice detectors. This cost about $100 million to build. It's 3,000 square kilometers. They have 1,600 of these detectors, which is very nice. They also have about 10,000 cows roaming free because they don't need much of the land. And I said it's a very nice experiment. One problem with doing this experiment is that these particles are very rare. So the particles we're interested in at the very highest energies, you notice this drops very quickly. So here at 10 to the 19, this is 1 particle per square kilometer per year. Up at the very highest energies, the really bizarre energies that make no sense, it's 1 particle per square kilometer per century. So once for every 100 years, right? And there's a lot of things we'd like to understand about these particles. For example, where are they coming from? Well, it's hard to understand what is out there making them if we don't even know where it's coming from, right? If you could, for example, pinpoint that all of these particles are being shot at us from a moon around some planet in a nearby star, wow, that would be fascinating. But we don't know where they're coming from because we just haven't seen enough of them. So, for example, these circles are 10 years of data. And these are not even only the highest energy. You have to lower the threshold to a little bit lower energy just to get enough data. And this is a map of the sky, and the circles are where we saw particles coming from, and the stars are the location of galactic centers that we think might be the source of them. And in 2009, this Auger collaboration thought that they had enough evidence to say that these galactic centers might be responsible. Since then, they've gathered more data, and they've discovered that it doesn't look like that's the answer. So we don't know where they're coming from because we just don't see enough of them. We don't have enough data. The problem is that Auger, while it's a wonderful experiment and beautifully run by smart people, it's small. I mean, it's 3,000 square kilometers, but the Earth is much bigger, right? The Earth is 5 orders of magnitude bigger. So what could you do? Well, you could build a lot more of these things. You could just make it bigger so you get more data and maybe learn where these things are coming from. But at $100 million a pop, this doesn't get cheaper if you build 10 of them or 20 of them or 100 of them. And there's not the appetite for a $1 billion science experiment out there in the halls of Congress. Imagine for a moment, though, if you could, right? What could you see if you could cover the whole Earth with these kind of detectors? Well, down here, where it's 1 particle per square kilometer per century, the Earth has a lot of square kilometers. So in 1 year, you could see 1 million of these particles. Wow, what we could learn about the universe if we had 1 million pieces of data at these very highest energies. That would be fantastic. Well, what you could do is you could just run for a very long time until your graduate students look like this, right? You could get 100 years of data, all right? But that's not using your smarts. So imagine you could design a fantasy experiment to answer this question. You wanted to get as much data as possible. Well, you would want it to be about the size of the planet, spread around on the ground. You don't want to spend a lot of money, so you want to use existing devices. You want to be able to upload the data wirelessly. You don't want to have wires snaking over the whole planet. You want to be able to control these things in case you want to change how they're organized. And then you want each one to be maintained, make sure it's usable, it has power, nobody's dropping it in the toilet, etc. And this might seem like a fantasy, right? But it actually exists. It's the network of smartphones in all of our pockets. As consumers, we've purchased more than 3 billion of these tiny computers. And each of these computers
has a camera in it, right? And that camera is good for lots of things, more than just taking pictures of your sushi. Behind the lens in the camera is a CMOS chip, which is how it takes the digital picture. And this CMOS chip is just a piece of silicon which works as a particle detector. And the phone, of course, has a little computer on it. We can program it. It has Wi-Fi for uploading data. And we at the LHC are very familiar with using little silicon chips to detect particles. In fact, the inner part of the detectors we surround the collision points with is nothing but silicon chips. Each of these is a big slab of silicon because silicon is an excellent particle detector. So we're very familiar with this technology. So what am I talking about? What would happen? How does your phone work as a particle detector? Well, imagine that this is the chip behind the lens in your phone, and you cover the camera so there's no light, and a particle comes by. Well, the particle can go through any covering you put over the camera lens, a piece of tape or your hand or whatever, even if it's in your pocket. These particles we're interested in can penetrate through most materials, and what it'll do is deposit a little bit of energy. So if you took a picture right at that moment when a particle was passing through your camera chip, then your picture would look like this. It would be a blank picture with one little dot from the particle. So this is what we're looking for. We're looking for evidence of particles passing through the chip behind your camera. So we thought, well, that's crazy. Can that actually work? Well, we have in the lab here at UCI a bunch of radioactive sources which shoot out high-energy photons at about the same energy you would expect to see from these showers from outer space. So rather than going out in the field and trying to see a shower, we thought we'd just try out in the lab. So one Christmas, I spent writing my first app for a phone, which was surprisingly easy to do, and because there's a million people out there with every problem already solved. And I wrote a little app just to test, can we see particles? And here's a little video of me trying it out. And the app is running on this device, and this is a radioactive source that shoots out high-energy photons. And the way the app works is every time it sees one, it puts a little splash on the screen. There you go. So once it starts detecting them, it makes these little splashes. Imagine the screen is like a puddle of water. I might try to make the particles look like they were flashing through it. And so clearly, when you bring it near this radioactive source, it's detecting the presence of those particles. So this was our first aha moment, like, wow, look, we can see particles with this tiny detector. That was a lot of fun. And we zoomed in and said, what do these particles actually look like? What do these images we're getting look like? So here's some of the first data we collected. This is just, these are just pixels. Each of these panes is one picture of data that we got. So often you see something like this, a little splash, a little splash, a little splash. Sometimes you see something like this. What happens here is that a particle comes in and it knocks off another particle, which then wiggles through the chip, leaving a little trail before it finally gets reabsorbed. So that was pretty cool. This convinced us we really were seeing particles, not just random noise. And then we were also interested in whether we can see other kinds of particles, like muons from space. So we fly back and forth to CERN a lot, which is in Geneva. So we gave one of these devices to one of our students, and he had it upright in the airplane on the flight, because at higher altitudes you also see more of these particles. And he captured this image here, which is you can see a particle traversing almost all the way through the picture. The phone was upright, and the particle just happened to slice all the way through the very thin chip and leave this very long path, which is very nice. And because we are particle physicists at a collider, we have access to beams of particles. So we have a muon beam at CERN, and we set up some of our phones just next to it. I mean, the beam is designed to do something totally different. We just took advantage of the fact that we could go in there, and we ran some devices here. And the beam shoots sideways, and this is the collected data. You can see there's a lot of tracks here from particles shooting sideways. So we convinced ourselves that we can see photons, we can see muons, so we can actually see these particles coming into the phone. And so we have an app. Here's what the Android app looks like. The first app I ever wrote. And then we had an undergrad here at UCI, very sharp undergrad, write the code for an iOS app. So we have an Android app and an iOS app, which is a lot of fun. And last year we actually won an award. It's called a Webby Award. People tell me it's like the Emmys of the internet. It was a lot of fun. There was a fancy award party with celebrities in New York City, etc. But then the question was, all right, so you've developed an app which can do science, which can see particles. Can you actually do science with it? Right? Is this something that's just like for fun, or is this something where we can actually learn something about the universe? And so that was the next question, is how many of these things would you need in order to actually do some science? So we did a bunch of calculations to help us understand how many phones you would need to have in order to see some actual particles from outer space. And so here, this plot here tells you the probability to see a particle from space as a function of the density of users on the ground. So this is 100 users per square kilometer, 1,000 users per square kilometer, 10,000 users per square kilometer. And this blue line tells you the actual population density of regions on the ground on the Earth. So there's a lot of places where you have 100 people per square kilometer, fewer where you have 1,000 people, and very few where you have 10,000 people. And what we learned was if we had about 1 million devices distributed however we wanted, then we could do real science. It takes about 1 million devices. Now, we didn't know when we started this project if we would need 100 devices to do science or 1 trillion devices if it was just totally infeasible. So learning that we needed 1 million devices to match the power of this $100 million experiment in South America, we took that as good news. We thought, well, 1 million devices is not crazy. Especially because if you go to Wikipedia and you ask, what are some of the densest places on Earth, you find out, first of all, none of them are in the United States, right? So the Philippines is a great place to do cosmic ray physics because there's 43,000 people per square kilometer. It's incredibly dense in Manila. And also they have more than 1 million people in this city. I mean, there's some of these cities that are very dense but very small, like some of these little French towns. But a lot of them are large cities with a lot of density. And so these are excellent places to see cosmic rays. Now, the reason we need high-density areas is we need people running the app simultaneously because the shower comes down from space and it spreads out about 1 square kilometer, and we need to see it in multiple phones at once in order to convince ourselves that we've really seen something and not just random noise. So this density is very important. Now, is a million users reasonable? Well, 1 million sounds like a large number, but it's small compared to the number of devices that are out there. So here's a projection from 2012 about the number of smartphones we should expect to have in the world. So in 2012, there were just over 1 billion smartphones, and they projected that in 2015, we would have over 2.5 billion. Question? How do you get the app? I'll tell you at the end. I appreciate your enthusiasm. So they projected we'd have 2.5 billion devices today. If you look it up today, we have more than 3.5 billion active devices. So 1 million is a tiny fraction of all the devices that are out there. And the number of devices is growing faster than anybody could imagine, right? I read a projection last year that by 2020, we would have 6 internet-connected devices per person. I'm not sure exactly what we're going to connect to the internet, our belt buckles and shoelaces, but that's the projection. So clearly, this is the direction that computing is going, right? And think about this. If we have 3 billion devices out there, each one costs a few $100, then we've invested a few $100 billion in this distributed computing platform. This platform is capable of doing science at an amazing scale, if only we used it, right? Mostly it's just used to take pictures of your grandkids, which is fine, but there's a huge amount of time when this network is just dormant at night, when you're sleeping, when you're not using it, and we could harness the power of this massive, expensive platform we've already built to do a little bit of science that could be really powerful. How powerful could it be? Well, we asked ourselves, how much science could we do as a function of how many people sign up? So here, this is percentage of the world which runs our app, so 10%, 1%, 0.1%. And this is essentially the effective area. This is how much science you can do. This is our competition, the $100 million experiment, this blue line. And focus on this dashed green line here, which is our most optimistic projection. This tells you that less than 1% of the world population participates, we match this $100 million experiment. Now imagine what happens if 10% of the world participated. Then we are 100 or 1,000 times more powerful than this other experiment. We could do science, cosmic ray science, at a level never done before. We have a new kind of device pointed out into space. We could learn all sorts of crazy things. So how many people is that? Well, just under 1% of the world population is about 45 million people. But it turns out the ones we really need to do the science are all in cities. If you have one guy out in the middle of Kansas running a phone, it doesn't really help you because you need to see the hits in multiple phones at the same time. So we really just need the high density areas, places like Manhattan or Manila. So if you only focus on those areas, you still need just about under 1% participation. That's only 6 million people. So I told you earlier we need about 1 million people. That's if we could organize it ourselves however we wanted. In terms of the actual distribution of people, then we'd need about 6 billion people to take into account where people actually live. There's a lot of problems left to be solved. For example, how do you actually see a shower on the ground? Well, what happens is the cosmic ray hits in the middle, and then you have a bunch of phones somewhere nearby. Some of them will register a hit, like, oh, I saw a particle. Other ones will not. They won't register a hit because there weren't that many particles there, or just because the phone happened to be off, or we don't have 100% efficiency in seeing those particles because the sensor in your phone is actually really small. It's less than a square centimeter. But when we get all this data, when we see the pattern of phones being hit or not hit on the ground, then we can tell what the shower looked like. But we have a much harder problem to solve than the experiment in South America. In South America, they have a regular grid. They've built it in such a way to make it easy to understand where these particles come from. And they have very fine timing, so they can see up to 100 picoseconds difference in arrival times between detectors, which means that they can see a shower wash over their detectors in real time. We don't. We have an irregular grid because we're just using people's phones, and we don't have nearly as precise timing. So we have different kind of reconstruction problems than they have. But we think we can solve these problems. We have some cool mathematical techniques to understand this data and extract the information. So we wrote this paper, and it came out about a year ago, and it caused a lot of discussion. Are these guys crazy? Could this really happen? And some disagreements. And we think we've convinced people that we're not crazy, that this idea really can work. So we have a collaboration of scientists led here at UCI. I have a bunch of graduate students. And the cool thing is that everybody here is just volunteering their time. Like, my day job is doing research at the LHC, but nights and weekends when I have enough energy, I work on this project. And there are several people who have come to me and said, oh, I'd love to help out. So Homer Strong is a grad student in computer science. Kyle Brody is an undergrad here at UCI, a physics major who wrote the iOS app. Jody Goddard is actually a random Android developer from the internet who's volunteering his time to improve our app. Rob Porter is one of my ex-graduate students who now runs his own company, and he's helping us develop a version that runs on laptops, etc. We have friends at UC Davis helping us out, a collaborator from NYU. This is Yandex, which is a Russian research lab, and they're participating. And then we also have collaborators in China. We need global coverage if we're ever going to do real science with this app. And the Chinese government is not very keen on the idea of an American group distributing devices in China to gather a bunch of data and send it back to the United States. It sounds a lot like spying. So we have local Chinese collaborators who are going to coordinate the data in China itself. So that's helpful. And we have a small grant from Amazon to help us pay for the data. Now, I sold you this device as basically free, which is true because we've already spent the money to build this platform. It already exists. But there is one area that does cost money, which is gathering the data. When I first started this project, I just had it running on a computer on my desktop. And as soon as we had more than a few hundred people running it, it quickly crashed because the amount of data coming in and the network traffic quickly grew. Then we realized if we're going to have a worldwide system, then we need to have a worldwide data collection system where you can upload the data from anywhere. And that's the cloud. So we need a data acquisition system that gathers the data that runs in the cloud at all times. And that's not cheap. Cloud is a big business these days. We think if we have about 1 million users, it might cost up to $10,000 or $20,000 a month in computing time. But we got a grant from Amazon, and they're paying for our computing, which is very nice of them. And some of my graduate students used to work in the startup fields and the internet, so they know what all these boxes mean, and we're able to write software to run in the cloud to gather this data, which is very helpful. And there's a lot of problems that still remain. So one of them, for example, is how do these things depend on the atmosphere? What happens when the particle hits the top of the atmosphere is it creates this shower, and how that shower develops as it goes through the atmosphere depends on things like the temperature and the weather and the pollution. So those are things you need to understand in order to understand what you're seeing. Another one is how much energy was in the initial particle. Well, the more energy in the initial particle, the more particles are created in the shower, the more things you should see on the ground. But you'd love to really know that you're getting this right. How do you know that when you measure something at 10 to the 20 that you've really calibrated this correctly? We'd love to have a calibration where we had a particle gun from space shooting us particles at known energies that we could measure, but of course we don't have that. Something I'd like to do is I'd like to set up our system using phones at the same location as the other system, the Auger system in South America, so we can take measurements at the same time as them and cross-calibrate each other's results. Another issue is that there's lots of different kinds of particles in these showers, and some of them we're more sensitive to than others. And there's lots of user challenges. We need people to participate in order to make this work. If people aren't excited about it, we just can't do the project. Are people excited? Well, we put out this paper last year, and it got a little bit of press. We've had some nice help from the people here putting it out. And in just a few days, we had 50,000 people sign up. And I think that there's a real group of people out there who are excited about physics and the universe and astrophysics and would like to feel like they're participating in physics. And so we want them to feel like they can join the project and help. Not just, would you lend us your phone when you're not using it, but would you join our collaboration? Would you be a scientist so you can feel like you actually are a member of the group? So there's a lot of excitement out there. To make it, to spread it around, we made it very easy. So the app is free. It's easy to install on your phone, and it runs automatically. So you don't need to turn it on every single night. You don't have to remember it. It notices when it's dark and you've plugged it into power, and if you just put it on your bedside table or wherever you leave your phone at night, the camera is facing down. That blocks most of the light, and the app notices that. It waits a minute to make sure you're not going to use it anymore, and then it just turns on. It launches itself, and it starts collecting data. In the morning, you pick up your phone like you normally do to check your messages, and it'll say, "Good morning, you had 77 muons last night." And then it'll just go into the background, and it won't run while you're walking around because it uses a lot of power. It's using the video on your camera, so it only runs when it's connected to power. And the idea is that it shouldn't bother you. You are donating your time and your device to us, so we should make sure to not ever bother you. So that's one reason why we haven't actually rolled it out to a very large community yet. We took the most enthusiastic 1,000 people in this list and sent it to them, and they're giving us feedback, we should do this, we should do that, because some people will want to run it in I downloaded it, I want to forget about it mode. Other people will be very excited about it. They want to interact with it. I want to see a picture of the particles I saw. I want to see how many particles I collected compared to my neighbors. So we have interactive things. We have like a leaderboard. There'll be prizes. Yes?
Can it work with what we call internet cameras?
Does it work with webcams? Absolutely, it works with webcams. And we have a version which runs on laptops now, because almost every laptop has a webcam. There's a different set of issues there, because with a phone, it's very natural to put it face up, camera down, and then it's blocked. With a laptop, a lot of people just leave their laptops open, and so the camera is not covered. And there's some privacy issues with basically turning on people's webcams in their house at night and taking data. There's some things I probably don't want to see. I think everybody should be blocking their webcams. Nobody should have an internet-connected camera open in their house all night long, but almost everybody does, which is sort of weird. So anyway, I think our plan is to distribute stickers people can put over their webcams just to alert them to the privacy issues, and then we could run it on laptops as well, which is a huge base we haven't even touched. Okay, yeah, right, so the app launches itself when the device is charging and is not being used. And then to motivate people, we have levels. We're trying to turn it into a little bit of a game. You collect enough particles, you get to level up. Here's one device that was been running for, this is a lot of seconds it's been running for, you can see. So it got promoted to the level of astrophysicist, et cetera. And we have lots of ideas for, it'll post to Facebook if you want it, to tell your friends how many particles you've collected. These sort of things to make it spread virally. So it's not something we're used to, right? I'm used to thinking about data and writing papers, not about writing a viral app. But there are also other uses for this data, right? We're talking about building a distributed set of devices that can measure particles anywhere in the world. And that's, of course, interesting from the point of view of cosmic rays. But there are also other interesting uses, like radiation. Most radiation that can harm your body comes in the form of these tiny particles. And we basically built a small dosimeter. In fact, there's a pane on the app that acts as a dosimeter that can measure your local radiation in real time. Now this is interesting because, as far as I know, nobody has a real-time worldwide map of radiation levels. And if there's some event, for example, Fukushima, we might all be curious, how much radiation is there in my house right now? Should I take my kids underground? Should I go into the mountains? What should I do? And when the Fukushima disaster happened, there was a lot of people who had this question. And there were a lot of articles that looked like this: Fukushima radiation to hit the West Coast. And you see this like explosion from Fukushima, and here's the West Coast, and you're like, oh no. And I mean, this is a real blog post, but if you look at this graph, what is it actually showing? This is a graph of the wave height of the tsunami, okay? It has nothing to do with radiation. And the reason they grabbed this picture is just because there is no such picture of the radiation. Nobody has a map of the radiation that's going across the world. Imagine you had 1 million or 2 million or 10 million devices constantly measuring the local radiation levels. Not only could you perhaps prevent yourself from getting cancer from radon, which kills 20,000 people a year in the United States, more than drunk driving or falls in the home, but you could also build a worldwide map of the radiation. So if Putin does a test in Mongolia, perhaps we could figure it out, right? There's all sorts of interesting things you could do with this data that we haven't even thought of. So we have people participating from around the world. As I said, we've only rolled it out to about 1,000 people who are hardcore beta testers. Here it's a little less than that, 600. This is from a few months ago. And you can we have a map on our webpage that shows you where data is coming in from right now, and then rankings by country. So you can see the US is our biggest country, the Netherlands, Great Britain, et cetera. But we have people from every continent except for Antarctica. I'm going to give one of these devices to Steve Barwick to take down there so we can cross that off our list. And if you're interested in the app, you can go to our webpage and sign up, and we'll send it to you when it's ready and bulletproof and very, very easy to use. If you're very, very eager and very enthusiastic, you could download the app right now if you have an Android device. Android makes it very easy to install these things on your phone, whereas iOS is much more protective. So for an iOS app, there's a lot more steps involved. But if you have an Android phone, then you can download it and install it right now. You take a picture of this QR code or just go to this URL or come ask me afterwards if you're interested in being one of the early beta testers. I'll give you a moment to look at that. So we're hoping to break some world records. The highest energy cosmic ray that was ever observed was 3 × 10 to the 20 electron volts. It was seen by Fly's Eye and Auger, and they call it the wow event because when they saw it, they all said, wow, oh my gosh, it's crazy. We're hoping to go even higher. We're hoping to go to 10 to the 21 to see particles at energies that nobody's ever seen before. Why has nobody seen them before? Only because nobody has had a big enough detector or run it for long enough. If we can build a detector that's big enough, these particles are there. They're washing over the surface of the Earth all the time. We're just throwing the data away. Instead of throwing it away, let's collect it. We're hoping to have the most expensive experiment ever. The $10 billion is spent on the Large Hadron Collider. We've already spent about $500 billion on this mobile computing platform of all of our devices. Gosh, let's use that to do something interesting. The longest author list ever. The collaborations from the LHC have about 3,000 scientists on them. Sometimes we write a paper that has 3 pages of text and 8 pages of authors, which is already ridiculous. But we want people who participate in this to feel like they're really members of this community. So anybody who lets the app run on their phone for long enough to get useful data will promote them to be an author on a paper that uses their data. And we wouldn't be the first to use internet users as authors on papers. There's a group from Harvard that were trying to solve a really difficult protein folding problem, which requires 3D spatial visualization and rotation. And what they did was they turned it into a video game, because a lot of these gamers, I don't know if you've tried to play one of these games recently, you have a joystick with like 6, you have a controller with like 6 joysticks and 9 buttons on it, right? It takes a lot of mental power to work your way through these worlds, and the video gamers are excellent at these kind of skills, so they put out a video game. And they had been working on it for 3 years. Within 24 hours, some video gamer had solved this 3D problem of protein folding. And so they put his name on their Nature paper. It was like 2 Harvard professors and some guy named Big Pimp 62. So we wouldn't be the first to have random internet users help us do science. But we really want to engage people. We want people to contribute and feel like they're really part of it. So in conclusion, cosmic rays are an enduring mystery. One of these big questions about the universe is what is out there, And anytime you have a clue that there's something out there you don't know about, then you want to follow that up. You want to say there's some messages being sent to us from outer space by people, by Martians, by some star, by some crazy new object we don't know. It could reveal something bizarre going on about the universe we don't know. And we can use the existing network of mobile devices to see ultra high energy cosmic rays, but we could also see something else. Anytime you build a new kind of telescope and point it out into space, you have the possibility to see something new. Why? Because space is full of crazy stuff. Every time we've built a new kind of telescope and looked out there, we've seen something amazing which blew our minds. So you build a planet-sized telescope and point it into outer space, you could see something new. For example, maybe there's some correlation between particles hitting Australia and particles hitting France. Nobody's ever seen that before because nobody's ever had a device that spanned the globe, or something I can't even imagine this morning we could see. But a lot of hurdles remain. I don't know if this is going to turn into the most exciting science project I've ever done, but it has been one of the funnest projects I've ever worked on. Thanks for your attention.
Looks like we have some enthusiasm.
Yes, they're very interesting and fascinating thing to do.
Thank you.
Regarding that 100 millisecond sort of timing resolution, I mean, the cell phone itself, the clock could be synchronized to the GPS, which would be to nanosecond accuracy. Is that an operating system thing, and would it be possible to get a hack or a information or whatever to get a timestamp that would give you, nanosecond accuracy?
Right, so the question is, how accurate could we make the timing? It's a really good question. You're right that GPS can have nanosecond precision. The problem with GPS is that it takes a lot of power to listen to these messages from satellites. So mostly your phone is not using GPS to get timing and location information because it uses too much power. Location information mostly comes from Wi-Fi. Your phone knows about which Wi-Fi networks are around, and Google knows where all the Wi-Fi networks in the world are, and so it can use the presence of local Wi-Fi networks to tell you where you are. And timing information mostly comes from the phone's clock. It can be improved with GPS, but that's very expensive. The other issue that limits us is that we're taking video, and video is at about 30 hertz, or 20 to 30 hertz. So the camera integrates for about 50 milliseconds before it gives you an image. And you can't tell when in that window that you took the picture the particle arrived, at the very beginning, at the very end. So unless your video is capable of taking faster data, you can't get faster than about 50 milliseconds.
Again, a limitation in the operation of the phone of the video.
That's right.
Would the high energy cosmic ray be so high that if you had a much shorter integration time, it would still catch it? So in other words,
Absolutely.
again, have some kind of hack in there that would use the chip and
Yes. So
Plug-in device.
yeah. So if you could rewrite the operating system or have lower level access to the operating system, you could get much finer timing resolution. Yes. But we're trying to write an app which can be used on millions of phones, so we can't rely on modifications to the operating system. We thought about doing a plug-in device, like something you plug into the headphone jack, but that scales very quickly the cost. Like imagine that cost $1. Well, now you have $1 million, right? And you have to distribute it. So, good questions.
When I take a picture of my grandson, most of it is sort of locally flat. Then if I had a Facebook account and posted it on Facebook, it could also post the location and the time of that. So somewhere out there is a huge universe of locally flat pictures with the location and the time attached. And granted, you have to use a lot of computing power to locate the non-flat places of those pictures. Wouldn't that be a way of getting data more quickly?
So existing photos. Yes, unfortunately, the existing photos are just one snapshot in time. So what we really need to see these things, you need a lot of photos being taken all at the same time. We need coincidence between several phones. So if you had a lot of people all taking a photo at the same moment, that might be useful. And it's really, really big, you're right. And the other issue is that we need essentially black images. We need the camera to be covered. So anytime you're taking a picture in the daylight, there's too much background for us to see these particles.
It's not locally flat. If you get hit by something that's going to completely saturate the pixel, it's going to show up.
Right, right. Yeah, it would be a lot of computing time, but it's something we can look into. It's a good idea, thank you.
actually get rid of these anomalies? How do you work around that?
We worried about that a lot. There's a lot of steps between the picture being taken and the data being supplied to us in the operating system. A lot of steps, and a lot of those steps are proprietary. We tried to ask Samsung, exactly what do you do to these images? They don't want to talk about it, right? Because they have a lot of noise correction. But we do see the particles, so we know that it's not killing them, right? And something we really need to understand very well is what fraction of particles that hit the phone do we see? So we can't know exactly what happens, but we can measure what the effect of it on our ability.
Don't tell Samsung, they'll correct it. They'll fix it, but you can't.
When an event occurs over how much area does the cascade spread out?
About a kilometer, square kilometer.
Can you review one more time what kind of density and time you need? So if there was 1 million people, they'd have to be in New York, or could they be spread over the U.S.?
You need about 500 people in a square kilometer in order to have sensitivity. So 500 people per square kilometer is the minimum density to be useful. And so Manhattan is much, much denser than that. Los Angeles is about that density.
And then the second part is, if there was a global night where everyone was told to do it, you might actually get one night with 100 million people across the world. Is that value, or is it really over the course of the year that you want this dense area in New York to be?
That would certainly be valuable. Absolutely, that would be valuable. I mean, you can measure it in sort of like phones times years. So more years or more phones, either one you win.
Question in the back.
You talked about how much power it's using, so people want data from how much data they receive in the hard.
Great question. How much data does it use? So first of all, we only upload via Wi-Fi, which should be free to everybody. And if you don't have a Wi-Fi network local, if it can't find one, it'll just save the data on your phone until it sees one and then upload it later, because we don't want to use anybody's cellular data. But the data rate is very small. I mean, these particles are rare. So you're uploading a few kilobytes a month. So it's very small. Another interesting question is the power usage. You plug it into the wall, it's going to use some power. How much does that cost? We don't want to rack up people's electricity bills. So we just did a quick estimate. It's cents per month. It's pennies. Electricity is cheap, fortunately, and this doesn't use that much, so it's pennies.
Can you talk a little bit more about the decimeter and how sensitive that is? And does that require so much power? And maybe we should all have that protection vertically?
Yeah, so the decimeter, we're calibrating it right now. The other uses, the science uses are simple because we can't ever hurt anybody. The dosimeter usage is a little more complicated because we need legal protection to make sure nobody hurts themselves, et cetera. We don't want people running out of the house in the middle of the night in a false alarm and tripping and hurting themselves, and then we're liable or something, and Ken has to use his whole budget to pay for it. So it's a little bit more complicated, but we're calibrating it. It seems sensitive. It seems like it can work to measure local levels. And the way I imagine it working is in an alarm mode. It's running in your house at night, and if there's a radon leak in your basement, it can detect it, and it can wake you up and go to a hotel or something. It seems to me like a lot of people would like to have a radiation alarm on their phone that will wake them up or alert them if there's a local radiation spike.
Can it pick up the noise from a smoke detector?
Smoke detectors do. Yeah, that's right. Well, each device would get calibrated to the local background levels because it knows where it is and what time it is, and it measures. I mean, there's radiation all the time, just at a background level. So it would look for a spike above that background. So the question is it better to have more area or more density? Well, the more density, then the more efficiency you have for lower energy showers. The more area, then the higher the rate you're going to get. So I'm not sure. Both have advantages. Thank you. Wow, great question. The question is, how well do you know where the phone is, the position uncertainty, and how important is that? Great question. So as I said before, GPS can be very accurate, but it's rarely used by the phone. And the Wi-Fi can get your location to within a meter or less, depending on the local area. We don't need to know the location to within more than a few meters. So Wi-Fi is precise enough. We've done some simulations. If you randomly smear the locations in our simulations by a few meters, it doesn't change anything about our resolution. So we think the position resolution is good enough. Plus, your phone is smart enough to guess where it is and to give you an uncertainty measurement. It has an uncertainty. It's like, I'm not sure, or I'm very sure. So it knows how well it knows what it knows, as Donald Rumsfeld might say.
Well, thank you very much, Daniel.